Welcome to The Explainer. Consider this your Quantum Computing 101 lecture, so grab a seat. Today we're taking a pretty wild ride. We're going to bridge that massive gap between abstract physics, hardcore math, and the literal billion-dollar hardware that's actively reshaping our world right now. If you've ever found yourself wondering how on earth we get from weird theoretical thought experiments to actual physical machines that absolutely crush traditional supercomputers, well, you're exactly in the right place.
Let's kick things off with a slightly provocative question. Why are our standard classical computers, the ones sitting on your desk or in your pocket right now, suddenly hitting a massive brick wall? I mean, these machines run on those trusty, deterministic zeros and ones, and they are incredibly fast. But when it actually comes to simulating the natural world at its most fundamental level, they're completely failing us. So why is that? To figure that out, we're going to use this actual university syllabus as our guide. Just like a real-deal introductory course, we're going to explore how early theoretical paradoxes evolved into today's absolute cutting-edge computational algorithms. It's really the perfect roadmap for our explainer today.
Here's what's on the agenda. First, the classical computing limit. Second, early paradoxes and Feynman's vision. Third, the quantum mathematical blueprint. Fourth, the 1990s algorithm explosion. And finally, number 5, modern quantum hardware reality. Let's get right into it.
Starting right off with Section 1, the classical computing limit, and specifically the simulation problem. Take a look at this little equation, 2 to the power of n. Back in 1981, Richard Feynman pointed out a massive simulation problem. If you want to simulate a quantum system, let's say a complex molecule for drug discovery with n particles, your classical computer needs 2 to the power of n resources. It scales exponentially. To put that into perspective, simulating just 300 quantum particles would require more classical bits than there are literal atoms in the observable universe. It's mind-boggling. This creates an uncrossable complexity gap for fields like materials science and cryptography, making these problems basically impossible for our classical machines to ever solve.
Which brings us to Section 2, early paradoxes and Feynman's vision, where we start rewriting the rules.
Okay, so our timeline actually kicks off way back in 1935 with Einstein, Podolsky, and Rosen. They introduced quantum entanglement as a paradox, famously kind of brushing it off as spooky action at a distance, just because it completely defied classical logic. Fast forward to 1964, and John Bell mathematically proves, via Bell's theorem, that these quantum correlations were in fact fundamentally non-classical. You literally couldn't explain them away with some hidden classical variables. And that realization right there laid the groundwork for a huge breakthrough in 1981, which is when physicists basically decided, hey, let's stop fighting this quantum weirdness and actually start using it.
That year, 1981, Richard Feynman famously declared, "Nature isn't classical, damn it." And he proposed this incredibly radical vision. If we genuinely want to simulate the true intricacies of quantum physics, we just can't use classical bits. It won't work. We have to build a machine that actually computes using the laws of quantum mechanics itself. It means leveraging things like superposition, entanglement, and interference as actual features, instead of treating them like annoying bugs in the system.
All right, let's move into Section 3, the quantum mathematical blueprint. We're stepping up to the chalkboard for this one.
First up on the board, we have vector spaces. Unlike classical bits that are strictly either a 0 or a 1, every single quantum state, a qubit, exists as a linear combination, or a superposition, of basis vectors inside a complex geometric space. Now, remember that nasty exponential limit we just talked about? Well, here, it suddenly becomes our greatest asset. The dimension of this vector space scales as 2 to the power of n. So think about this. A 53-qubit system isn't just 53 numbers. No, it is a 9 quadrillion dimensional space. It's wild to think about, but this exponential state capacity is the absolute bedrock of quantum parallelism.
Second, we've got operators. If vector spaces are the canvas where our data lives, you can think of operators as the brushes we use to actually manipulate that data. Mathematically, these are represented as unitary matrices that map vectors to vectors. Physically, they represent our quantum gates, things like the Poly-X or Hadamard gates. Now, what's absolutely vital to understand here is that these operations are fundamentally reversible. They have to be to preserve those superfragile superpositions of our quantum states as they evolve throughout a calculation.
And third, we have inner products. Written in that really elegant Dirac bracket notation that physicists everywhere use, an inner product measures the geometric overlap between two quantum states. So why does this matter to us? Well, it's all because of Born's rule.
The inner product directly dictates the exact probability of getting a specific classical outcome when we finally force the quantum system into a measurement. You can think of it as the mathematical bridge connecting our infinite quantum superpositions to the definite classical answers we actually need to read out at the end of the day.
And looking at this, it's just brilliant how perfectly these abstract mathematical concepts translate directly into physical hardware. Your vector spaces? That's the physical state capacity of the actual qubits sitting inside a freezing cold dilution refrigerator. And those unitary operators? In the real world, they are physically implemented by firing highly calibrated microwave pulses to control those qubits. Finally, the inner products represent your final measurement readouts, the actual data extraction at the very end of the quantum circuit. I don't know about you, but I think it's a truly beautiful moment when you realize just how cleanly the math maps onto the machine.
Moving right along to Section 4, the 1990s algorithm explosion, where we finally put all this math to work.
The pacing of the timeline here is just wild. I mean, in just over a decade, we jump from David Deutsch formalizing the theoretical quantum Turing machine back in 1985 all the way to Peter Shor in 1994. Shor discovers an algorithm that can factor large numbers in polynomial time, which essentially proved that quantum computers could straight up break modern internet cryptography. And then literally 2 years after that, in 1996, Love Grover discovers a quadratic speedup for unstructured database searches. We went from abstract physics debates to world-changing algorithms in under 15 years.
So, the really crucial question is, how do these algorithms actually achieve this massive speedup? Well, a great way to think about it is this. Classical computing is basically like searching a giant library by pulling out and reading just one book at a time. It's tedious. But quantum computing, by engineering those vector spaces and unitary operators we talked about, it can explore all the possible answers simultaneously in superposition. It's literally like reading every single copy of a book at the exact same time. And then, here's the magic trick, using wave interference to mathematically cancel out the wrong answers and amplify the right one.
And that brings us to our final part, Section 5, Modern Quantum Hardware Reality, the ultimate realization of Feynman's dream.
Decades of theoretical work have all built up to this truly staggering number, $30 billion. That's 30 with a B. That is the estimated global investment in quantum R&D from governments and the private sector as of 2024. This massive influx of capital is what's funding powerhouses like IBM, Google, and IonQ to actually build the physical implementations of those operators and vector spaces. They are literally translating Richard Feynman's 1981 dream into real-world silicon, superconductors, and trapped ions.
So you might be asking, why throw billions at this? Well, because real physical machines are finally crossing the threshold. Case in point, in 2019, Google's 53-qubit Sycamore processor officially demonstrated quantum supremacy. It completed a highly specific computational task in just 200 seconds. A task, by the way, that would take a state-of-the-art classical supercomputer roughly 10,000 years to crunch. And today, we've got processors like IBM's Heron and Google's Willow pushing well past the 100-qubit mark. The target applications here are absolutely immense. We're talking simulating life-saving drugs down at the molecular level, optimizing incredibly complex global logistics networks, and completely supercharging the next generation of artificial intelligence.
So we've walked the entire timeline today, from Einstein's early spooky action skepticism to Feynman's bold paradigm-shifting vision, straight through the beautiful, complex geometry of vector spaces, and all the way up to today's billion-dollar superconducting hardware. I want to leave you with this final provocative thought. We've decoded the fundamental physics, we've mastered the mathematical blueprints, and right now these quantum machines are literally booting up. The exponential computing power of nature itself is finally at our fingertips. The only question left is, what will you simulate first? Thanks so much for joining me on this explainer, and I'll catch you next time.